So let's use our concept of impulse to solve a problem. So take a moment to go through the statement of this problem. We have a stuntman, Jackie Chan. He's got a mass of 60 kilograms, and let's say he goes off the top of a 20-meter building, and suppose he starts at rest. He jumps off the top of the building and lands on a piece of foam below. And when he lands on a foam, obviously he's got some velocity with which he hits the foam, right? But then the foam deforms, and let's say it takes 0.5 seconds to deform before finally bringing Jackie Chan to rest, right? So we want to find the average force acting on Jackie in the 0.5 seconds. Of course, in order not to harm the stuntsman, we want this, average force to be small. We shall see that because this foam deforms, taking some time, this causes the average force to be small, and this is basically the reason why one jumps on a foam in order to avoid injuring oneself. Okay, so let's look at what's going on here. We have a building of some height, let's say h. Here, of course, h is 20 meters. You have some person, Jackie Chan. Let's model him as a particle, right? So he starts from here with a initial velocity of 0, and of course then he is in free fall, right? So he freely falls a distance of h, so that what's his final velocity just when he hits the ground, or well, the piece of foam at the ground. So just when he reaches the foam, his velocity would be given by v square equal to u square plus 2as. This is a formula that holds for uniform acceleration, right? Constant acceleration. So with u equal to 0, which was his velocity at the start, we have, and of course a is g, the acceleration of free fall, we have v equal to root 2gh. Of course h is s, the height through which it has fallen. In any case, so that's the speed at which he reaches the foam. What happens after that? So after that, what happens is that the foam starts to deform and slowly bringing him to rest. So if the particle was here initially, right, it was here initially with some velocity, this v equal to root 2gh, the foam deforms, finally bringing him to rest here. In this 0.5 seconds, what happens? Of course, Jackie Chan had a force acting on him, which was mg, and that keeps acting on him. But now that he is in contact with the foam, as soon as he comes in contact with the foam provides a force on Jackie Chan, which is the normal reaction force, right? And this normal reaction force changes with time. In the 0.5 seconds it changes, and of course finally the normal reaction force is equal to mg, because finally the body comes to rest, and we know that when a body stays at rest, then the net force on it must be 0, right? So we want to find, obviously in the 0.5 seconds in which the normal reaction force goes from 0, no normal reaction force, to a final value of n equal to mg, the net force acting on the body has a very complicated profile. So we want to find the average force that's acting on the body in these 0.5 seconds. To do that, we find it best to evaluate first the impulse acting on the body in the 0.5 seconds. So obviously we start with the initial momentum when the body has just reached the foam, so we can, which is at this point, right, when it just reaches the foam, we would have p initial, the magnitude of the initial momentum would be just, well, mv, right? But then that's just m into root 2gh. That's the initial momentum. Suppose we wanted to write that as a vector. How would we do that? Well, you could choose a unit vector along the positive y-axis or upwards, vertically upwards, let's say, in which case, because the velocity was downwards directed, we would have P initial is minus mv j hat, and that would be minus m root 2 gh j hat. And what's the final momentum? Well, finally the body comes to rest after 0.5 seconds, so that the P final is just 0, in which case the impulse acting on the body in the 0.5 seconds is just Pf minus Pi, which is m root 2 gh j hat. So the impulse acts towards the positive y-axis direction. Alright, that makes sense because the momentum quickly becomes 0 from some initial value, right? And the momentum was initially downwards directed. In any case, how can we find the average force? What do we have? We have, by definition, the impulse in the 0.5 seconds is, let's say you have an initial time of 0 to 0.5. We have to do this integration of the force in this time, and that gives me, as we said, m root 2 gh j hat. Because it's a one-dimensional motion, it might be best to absorb these vectors. Let's just deal with the magnitudes. So the magnitude of the impulse would be given by the magnitude of the, because the force is one-dimensional, the integration of f dt is root 2 mgh. So graphically, what does this look like? Like we said, the force, right, has a complicated profile in the 0.5 seconds. It starts with mg, but then you have a normal reaction force that reduces the total force. It acts upwards, and finally after 0.5 seconds the net force on the body becomes 0, right? So it's got a very complicated looking plot like this in real life, because the foam behaves in the real world in a complicated way. How can we find the average force in this time 0 to 0.5? So of course, impulse is basically this area, right? Impulse is this area. Let's consider another figure where we can reproduce the same area, right? We can have something like this. Let's consider a F average such that the area under this rectangle is precisely equal to this one, okay? So F average in that case should be somewhere between the maximum value of force here and the 0 value of force at the end. But anyway, let's say, so J equal to 0 to 0.5, right? So J equal to 0 to 0.5, an integration from 0 to 0.5 of f dt. But let's say the result of that, which is this area here, right, is precisely equal to the area of some F average into 0.5. Well, 0.5 minus 0, which is 0.5, right? So that, what's F average then? We have F average equal to integration of f dt by 0.5, right? Well, or in other words, in the most general case, what you have is basically, in general, F average equal to the impulse, the average force exerted on a particle in the time interval from t1 to t2 is given by the impulse just divided by the time interval, okay? which is precisely what we did over here, where the time interval was between 0 to 0.5. Well, we know the result of this integration just because we know the change in momentum, right? So we have F average equal to, we had m root 2gh as the result of that integration. We found that just by evaluating the change in momentum by this 0.5, right? And that should give you the average force. If you look at this formula, it becomes clear that these 0.5 seconds, which was the time that the particle took to change from a very large initial velocity to a final velocity of 0. If we keep increasing this, then the average force keeps decreasing. And that's basically why jumping on a foam is safe. The foam causes this time to increase because the foam takes some time to deform, right? So in terms of impulse, we are able to understand why things like a foam are easy to jump onto rather than the hard ground itself. Alright.